In this video, we will be looking at bond polarity and electronegativity. Specifically, we will be interested in the degree to which electrons are shared between two atoms along a chemical bond. Chemical bonds are generally broken up into three different categories based on how the electrons are being shared between various atoms. We can have ionic bonds. Those occur typically between a metal and a nonmetal. And in these bonds, an electron is transferred between the two atoms in a chemical bond. The cation will give up an electron to the anion. The next category are covalent bonds. Covalent bonds occur between two nonmetals. In covalent bonds, electrons are being shared as opposed to transferred between two atoms. So some of the time they will spend around one of the atoms, and the rest of the time they will spend around the other atom. This is as opposed to ionic, in which the electron completely moves from one to the other. The last category are metallic bonds. Metallic bonds occur between two metals. In a metallic bond, the electrons are pooled between all of the atoms. So you have a sort of a communal sharing of the electrons in a metallic substance. We will not be really concerning ourselves with metallic bonds in this particular chapter. We can think of non-metallic bonds, those that are ionic or covalent, as falling along a spectrum, with ionic bonds at one end, in which the electron is completely transferred from one atom to the next, and covalent bonds on the other end of the spectrum, in which the electron is spending equal time around the two atoms. Most bonds have some degree of sharing and some degree of ion formation to them, meaning that the electron, if it spends a lot of its time around one of the two atoms, it ends up looking more like an ion than an equal sharing that you'd see in a purely covalent bond. These bonds are classified as covalent if the amount of electron transfer is insufficient for the material to display what we would classically think of as ionic properties. If the sharing is unequal enough to produce a dipole in the bond, then the bond is classified as a polar covalent bond. Polar covalent bonds occur when you have two unlike atoms, meaning different elements, and will result in an unequal sharing of the electron. For a bond to be considered polar covalent, one of the atoms will need to pull the electrons in the bond closer to its side. This will result in a larger electron density on that side than on the other. As a result, the polar covalent bond has some bond polarity. The end with the larger electron density will get labeled as a partial negative charge, and the end that is electron deficient gets a partial positive charge. Note that these are partial negative and partial positive, not full negative and full positive like you would find in an ionic bond. The way that we can determine ahead of time whether we think a bond will be polar or not is to look at the electronegativity of the atoms involved in the bond. Electronegativity is the ability of an atom to attract bonding electrons towards itself. The higher the electronegativity, the more it will pull on an electron. The larger the difference in the electronegativity between two atoms in a bond, the larger the polarity of the bond will be, with the negative end being pointed towards the more electronegative atom. So if we look at an example of hydrogen and fluorine, fluorine is the most electronegative atom on the periodic table. It has an electronegativity of 4. So if we bond it to something like hydrogen, which has an electronegativity of 2, we have a large difference between the two values, which will result in the electrons spending virtually all of their time around the fluorine and very little time around the hydrogen. Because that electron is being pulled towards the hydrogen, you'll get a positive side aligning with the hydrogen and a negative side aligning with the fluorine. The way that we typically write out one of these bond dipoles, where you have a plus end and a minus end, is by putting a plus and then an arrow pointing in the direction of the negative side. The general trend in electronegativity along the periodic table is that as you go up and as you go to the right along the periodic table, things become more electronegative. So the most electronegative atom is fluorine. The least is francium. Noble gases are not assigned an electronegativity value because electronegativities are defined as the pull of the electrons towards the atom in a chemical bond, and most noble gases do not form chemical bonds, and so they do not have an electronegativity to them. This is generally the opposite trend that you'll find for the atomic sizes. The atomic sizes, if you remember, decrease as you go to the right and as you go down. So the electronegativity is the opposite of that. Electronegativity increases as you go up and to the right. Going back to the idea that our non-metallic bonds, those that are ionic or covalent, fall along a spectrum, we can bring in the idea of electronegativity to better quantify that spectrum. On one end of the spectrum, you could have where the two atoms are the same, and so the electronegativities, when you subtract one from the other, would give you a value of 0. If this is the case, where the difference in electronegativity between the two bonded atoms is 0, the bond is called a pure covalent bond. This involves the equal sharing of the electrons in the bond. We could also have something that's still on the far left side of the spectrum, where the difference in electronegativity between the bonding atoms is between 0.1 and 0.4. We call these non-polar covalent bonds. It is still a covalent bond, and it is still nonpolar, but it is not a complete equal sharing of the electron. The electron will spend a little bit more time around the more electronegative atom, but not enough that we would see polar behavior. If the difference, however, in electronegativity is larger, between 0.4 and 2, we will call these a polar covalent bond. It is a covalent bond that exhibits a polar behavior, so it has a plus end and a minus end. This results from the unequal sharing of the electron between the two atoms in a bond. In terms of where we are on the spectrum, we are on the left to middle side of the spectrum. So the electron is still moving between the two atoms, but it spends a lot more time around one side, the negative side, than the other, giving us a sort of a plus end and a minus end. So we have a dipole. So we have a plus pole and a minus pole, two poles giving us a dipole. If we get beyond a difference of 2, then the electron has essentially been transferred from one to the other. If the difference in electronegativity between the two atoms in a bond is larger than 2, we start classifying those as ionic bonds. At the 2 side of the spectrum, the electron will still transfer back and forth between the two, but it spends such a large amount of its time on the negative side that it is essentially continually there. For our bonds, we can also quantify the extent to which we have a plus end and a minus end by looking at our dipole moment. The dipole moment, which will be represented by the Greek letter mu, is a measure of the bond polarity, the degree to which we have a plus end and a minus end. The term dipole is not actually one of chemistry. A dipole is any material that has a plus end and a minus end. However, in chemistry, our concept of a dipole moment, it is directly proportional to the size of the partial charges, which will be represented by the variable q, and directly proportional to the distance between them, which will be represented by r. So the dipole moment would be our q times our r. Q would be the size of the charge, whether it is a plus 1, plus 2, minus 1, minus 2 charge on our atoms. And then r would be the distance or the radius of the bond. The unit that we will use for dipole moments are the dBi with a symbol of d. So if we have a difference of electronegativity between two atoms of 0, then our dipole moment would be 0. Right? The electron does not spend more time around one than the other. An example of this would be chlorine. Cl2, because both atoms are the same, neither one has a larger electronegativity than the other. We could look at ClF. Fluorine is the most electronegative atom, and so if we take a chlorine, bond it to a fluorine, the fluorine will pull the electron density towards it. This gives us an electronegativity of 1 and a dipole moment of 0.88. So this would be a bond that has a fairly strong dipole. We can now look at sort of the end of our covalent spectrum, taking a hydrogen, bonding it to a fluorine, giving us an electronegativity, or a difference in electronegativity, of 1.9. At about 2, we start calling it a ionic bond. So 1.9 is a fairly polar bond. And this gives us a dipole moment of 1.82. This is a very strong dipole. If we look at an ionic bond, like lithium fluoride, lithium is a metal, fluorine is a nonmetal. Fluorine is very electronegative, lithium is not. And so the difference between the two in terms of electronegativities is 3, which gives us a very large dipole moment of 6.33. So this bond would be very, very polar. In fact, it's an ionic bond. You have a plus end and a minus end. The plus end is the lithium, the minus end is a fluorine, and the electron is completely transferred from the lithium to the fluorine, giving you a very strong dipole for the bond.